there! We looked today in class at optimization problems. We got through what I would term kind of the more basic level optimization problems, and then the next time you're in class we'll do some more complex ones. The purpose of optimization problems is to determine minimum and maximum values, and we used this already in Unit 3 when we were looking at relative maxes and minimums. So when you think about what we did first when asked to find a relative maximum and minimum, our first two steps were to take the derivative and then to set that derivative equal to 0 to solve. And we did that kind of similar thing with absolute maxes and mins. When we got to points of inflection on concavity, you did it to the second derivative, right? But that's what you're going to see again here in optimization. Now there's stuff, of course, that comes before that, but essentially that's the procedural sort of concept behind optimization. So I have some helpful steps written out here. Number 1, you'll identify your quantities, sketch your scenario out. Number 2, write a primary equation. The primary equation is what we are looking to maximize or minimize within the context of the problem. And of course it might not say maximize or minimize, it might say something like largest or smallest or greatest, as small as possible, something along those lines, something that implies maximize or minimize. But that's going to be your primary equation. Step 3, we're going to reduce our primary equation to having one single independent variable. The reason we do that is because most equations, when you write that primary equation out, you're going to have more than one variable, which complicates taking the derivative. If we can get that primary equation so that it only has one variable in it, okay, then our derivative is really straightforward. Okay, and so that's what we're looking to do, get that primary equation into one variable. And this is where we use our secondary equation. Secondary equation would be a given fact, or potentially in some cases you'll literally be given an equation and that is your secondary equation. But it'll be some other given piece of information that allows me to manipulate to solve for a variable. Okay? So once you've done that, you'll substitute it back into the primary equation. At that point, you're going to take the derivative of your primary equation, you're going to set it equal to 0. Because remember, we're finding maximums and minimums. And then number 5, you're solving for all desired quantities, keeping in mind plausible domain. When we're talking about plausible domain, this would be, for example, if you were looking at side lengths of a box and you're trying to maximize volume. Well, a side length wouldn't be, for example, -5 feet long. So if you got as an answer, -5 and +5, well, you're going to disregard the -5 piece because that just doesn't make sense. You can't have a -5 foot box or a length of a box, right? Okay, so that's what plausible domain is. So we did, depending on the class, kind of somewhere between 5 and 6 problems. So I've gone ahead and selected here 5 that I'm going to be using to demonstrate. What we did in your specific class is on my website, so that you can reference that. My encouragement for you, like with the related rates when we were working through that, if you need to kind of follow through with this first example as we go through example 1 and then pause it and try example 2 on your own, start it again. What we did in class was kind of did a step-by-step, so that could be something you do when you get to example 2. So after we've watched through example 1, pause example 2, see if you can sketch it first, and then start it again and check your sketch and identifying your given variable. Then pause the video, see if you can write a primary equation on your own. Then start it, check your primary. Right? Pause the video, see if you can write the secondary, etc., etc. And just go step by step through it. You might find that more helpful, just so you don't get to the end of the problem and have worked the entire thing incorrectly and then start the video, have to erase it all. So. But again, I would challenge you, take that ownership, pause the video, try these on your own, making sure that you're actually assessing, am I understanding the material? Okay? So here we go. Example 1, we are finding the dimensions of a rectangle whose area is 1,000 meters squared and whose perimeter is as small as possible. That's my maximize, minimize phrase right there, as small as possible. In this context, we're looking to minimize. Okay, so step 1, we're going to identify all of our given quantities and sketch our scenario. In this case, we've got a rectangle. And I'm going to go ahead and call my rectangle sides X and Y, which means on the other side we will also have X and Y because it is a rectangle. And we are told that for this rectangle, our area is 1,000 meters squared. Okay, so that's step one. Step two, we're going to write a primary equation for the quantity that is to be maximized or minimized. In this case, my minimized is my perimeter. So my primary equation in this case is going to be the perimeter. And primary is always what's being maximized or minimized. We're looking to minimize perimeter. Okay, perimeter for my rectangle is going to be 2x's plus 2y's. Okay, so you can see here we have two variables. This is where step 3 comes in. We want to get this equation either entirely in terms of x or entirely in terms of y. Okay, so that's where we need a secondary equation. Okay, my secondary equation is going to be some sort of given fact. In this case, my given fact is that my area is 1,000 meters squared. And so I'm going to go ahead and write that. My area is 1,000 meters, and area for this rectangle is xy. Okay, the purpose of this secondary equation is now I can solve for a variable to plug it back in. And it doesn't matter which variable you solve for. Sometimes there's going to be one that is more efficient. We'll look at some of those. But in this particular case, it really doesn't matter. Neither one's going to be faster. You just choose. So I'm going to go ahead and solve for x. Okay. So if I'm solving for x, that means dividing y over to the other side. So this would be 1,000 over y. Okay, I can now plug this 1,000 over y into my x's spot right here. Okay, so we have perimeter equals 2 times x, which x is 1,000 over y, so it's 2 times 1,000 over y, which is 2,000 over y. And that's step 3. Okay, step 4. Now that we've got our primary equation with one variable, y's in this case, okay, we are going to take the derivative and set that equal to 0. Okay, 2,000 over y. I'm going to go ahead and just rewrite this just off to the side just so I can look at it. This is the same thing as 2,000 y to the negative 1. Okay, let me zoom back on that. I wrote that a little small, sorry about that. Okay, so I just rewrote this 2,000 over y as 2,000 y to the negative 1, so I could take its derivative with power rule. You could use quotient rule technically. Both would be about 2 steps. Okay, so power rule, I'm going to go ahead and bring down that exponent. So we have negative 2,000, subtract 1 from the exponent. And the derivative of 2y is 2. And then I'm going to go ahead and rewrite this negative 2,000 y to the negative second as negative 2,000 over y squared. Okay, so that's 4. We took the derivative. Okay, step 5. Now that we've taken the derivative and set it equal to 0, we're going to solve for our desired quantities, keeping in mind plausible domain. In this particular problem, my desired quantities are my dimensions, so I want x and y. Okay, well, I have that 0 equals negative 2,000 over y squared plus 2. So I can solve for y there. I'm going to go ahead and add this 2,000 over y squared over to the other side, which gives me 2,000 over y squared equals 2. I'm then going to multiply both sides by a y squared to get that y squared out of the denominator. Okay. Then I'm going to divide the 2 over. And take the square root. Remember, when you take the square root, it is plus or minus. Okay, keep in mind plausible domain though, right? We're finding dimensions of a rectangle. Is it possible for a rectangle to have negative root 1,000 as a length? No. And so we're going to disregard that negative piece. So my y in this case is 10 root 10, or root 1,000. Okay, and then my units in this case are meters. You also could do its corresponding decimal, as long as it was accurate to 3 decimal places. My only warning with doing the decimal is make sure that when you take this next step that we're about to take, use a lot of the decimal, use the entire decimal. Don't round and use the rounded version, right? If you use the rounded version, you might skew your final answer. Okay, because the last step here, we found y, fantastic, but we also need to find the other part of our dimension. They want the dimensions, right? So we need x as well. Okay, well if I want x and I have y, I find that by plugging it in. Right here in my secondary, I have x equals 1,000 divided by y. Okay, and so if I come over here and I do x equals 1,000 divided by my y, I get 1,000 divided by 10 root 10. Okay, which is the same thing. Okay, when you simplify 1,000 divided by 10, and then if you were to rationalize the denominator, you would get 10 root 10. Again, meters for units. Okay, so that's optimization. Okay, so let's go ahead and do number 2 next. Number 2, we're finding the dimensions of a rectangle whose perimeter is 40 inches and who has a maximum area. Okay, so again, my recommendation, pause this video kind of step by step, try it on your own. Okay, I'm just going to keep working through it, so you're going to need to pause it when you're ready. Find the dimensions of a rectangle whose perimeter is 40 inches. Okay, so let's go ahead and start with drawing our rectangle here. I'm going to go ahead and still use x, y, as my variables. Okay, and in this case, perimeter is 40 inches. Okay, I next need to figure out what's my primary equation, remembering that primary equation is what's being maximized or minimized. In this problem, I'm looking to find maximum area, so area is going to be my primary. And area of this rectangle is xy. Next up, I want my secondary equation, so I can reduce this primary equation to only one independent variable. So secondary. Secondary equation is some sort of given piece of information. In this case, I'm given that perimeter is 40 inches. Okay, and perimeter of this rectangle is 2 x's and 2 y's. Okay, again, it does not matter which one you solve for. You can solve for x or solve for y. I'm going to go ahead and choose to solve for x again. So I'm going to subtract this 2y over to the other side. And then I'm going to divide that 2 over. So we get 20 minus y as my x. And that then is what I'm going to plug in here. Okay, next step, now that you've got your primary equation in terms of one variable, you're going to take the derivative and set it equal to 0. Before I take my derivative, I'm going to go ahead and distribute that y into the 20 minus y. This is where I'm going to take the derivative. You could do product rule up above if you wanted to. The derivative of 20y is 20. Derivative of y squared is 2y. Okay. Last step, solve for the desired quantities in this problem. Those are the dimensions. So we can solve for y here. We have 0 equals 20 minus 2y. I'm going to go ahead and add this 2y to the other side. And then divide that 2, which means y equals 10. And in this problem, my side lengths would be measured in inches. Okay. For my x equals, well, under my secondary equation here, I have x equals 20 minus y. So x equals 20 minus my y, which is 10, which means x is also 10 inches. Okay. We're going to do 3 more of these. Okay, example 3. we need to enclose a rectangular field. We have 500 feet of fencing. A building already encloses one side. Determine the dimensions that will enclose the largest area. Okay, so here we go. We have our rectangular field with a building on one side. Okay, so what's important about the building? Well, if there's a building there, you don't need to fence that side. And so when I'm talking about my 500 feet of fencing, that side isn't going to be included in that 500 feet, right? You don't need to fence where there's already a building. And I'm going to go ahead and call these X and Y again. Okay. Here we go. Primary equation. Remember, primary is what's being maximized or minimized. In this problem, we're looking to find the largest area. Maximum area, maximized area. So area is going to be my primary. And in this case, area would be XY. Next step, find my secondary. Again, secondary is some sort of given piece of information. In this case, we were given that we have 500 feet of fencing. Remember, when you're constructing this secondary equation, you don't need to include the building, right? We wouldn't fence on the building side. So in this case, my fencing would be an X, a Y, and another X. 2 X's and a Y. Okay, we're going to solve for a variable. In this case, it still doesn't matter for the record which variable you solve for, but I would probably recommend solving for y with this particular one because it's only one step, right? Y is already isolated, practically. As soon as I subtract the 2x, I'm done. If you solve for the x, you're going to have to subtract the y and then also divide the 2. Okay, it's 2 steps. Again, it's not that much more time, so if you want to solve for the x, that's totally fine. But we're in the business of trying to save time where we can. Every couple seconds helps. That might be a second that when added to another one means you have that much more time on a problem that you would need to spend more time on, right, in terms of the AP test. Okay, so I'm going to go ahead and subtract the 2x over. I'm going to solve for y. And so that's what I'm going to be plugging into my y spot here. Okay, now that you've done that, step 4, we're going to take the derivative and set it equal to 0. Again, I'm going to choose to distribute first instead of doing product rule. And so then when I take that derivative of 500x is 500. Derivative of 2x squared is 4x. With this particular problem, we're looking to find the dimensions. So I can solve for x here, and then plug it in to solve for y. So I have 0 equals 500 minus 4x. I'm going to go ahead and add that 4x to the other side. And then divide that 4 over. When you divide that 4 over, you get 125. And this time, side lengths for this problem will be measured in feet. Okay. Y equals then, because they want both dimensions, y from our secondary equation equals 500 minus 2x. So we have 500 minus 2 times my x, which is 125, which is 500 minus 250. 2 times 125 is 250, which gives me 500 minus 250, which is 250. And then units are feet. Okay, let's do 2 more of these. I'm actually going to skip number 4 for now. We'll go ahead and skip to number 5. Okay, we're going to do 5 and 6 here. 5 and 6 are very similar. My recommendation, because these are slightly different than the ones we just did, would maybe be to follow along with me on number 5 and then do like what you did on those prior problems for number 6, which is kind of pause the video, do a step, start the video to check, then do the next step, etc., etc. Again, so you can practice it on your own, evaluate whether or not you're actually understanding what we're doing. Okay, so in number 5 here, we are given, or we were asked, Which point or points on the graph of y equals x squared plus 1 is closest to the point 0, 2? Okay, there's not an especially good picture to draw for this particular one. So this is where the words are going to come in handy, because we don't know specifically from the words what equation we're trying to use. Let me rephrase that. What I mean is, in those prior problems where they said, you know, find the largest area. Area was your equation, right? Like, they literally gave you the word for the formula you're going to be using. In this particular case, they don't actually use the word for the formula we're going to be using, and so you need to kind of think about, what does it mean to be closest to? Because that's a maximize, minimize, right? Closest, it's like largest, smallest, closest. The question is, what are we measuring when we're talking about being closest, right? So think of like being the closest to someone, right, compared to another person, right? What are we measuring there? We're measuring distance, right? Closest is a measure of distance. And so distance is going to be my primary equation in this one, because that's what I'm looking to maximize, or in this case, minimize, right? Minimize that distance. Okay, so I'm going to write the distance formula just across the top here. We did this on our previous notes day already, but just so we have it here to reference. Distance is x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Okay, so my primary equation in this one, distance equals, we don't want to use just this distance formula though, right? Because we're concerned about a very particular distance. We're concerned about the distance to this point, 0, 2. And so I'm actually going to be plugging in 0 into my x and 2 into my y to create a very particular distance formula. Okay, so x minus 0 squared, which is x squared, and then plus y2, or y minus, and then instead of writing y1, we're going to write that 2. We're plugging the 2 into that spot there. So y minus 2 quantity squared. That's my primary equation. Okay, secondary equation then. Again, secondary will be given to you in some way, shape, or form, a given fact, or, as in the case of this particular problem, we're actually given the equation itself, y equals x squared plus 1. Okay, at this point, you again have that choice. Am I going to plug in y or x? Am I going to solve for y, solve for x? I have a slight advantage here in knowing what's going to be the step after this. So let me just let you know now. We are going to end up needing to manipulate this inside the square root before we take the derivative. Right, like we're going to end up needing to FOIL this y minus 2 quantity squared out. That's going to make it so that it's just a singular chain when you take the derivative, as opposed to a double chain. Okay, and so this is just my strategy. Obviously this is already solved for a y, and in some cases I would just take this x squared plus 1 and plug it in. In this particular problem, I actually don't, only because I also always am looking to see, is there something else I see kind of matching between my primary and my secondary equation. Obviously we see a y located in both spots. And so if I don't immediately see some other matching piece, I would go ahead and take this x squared plus 1 and stick it in. Okay, but I also see this x squared. See how there's an x squared here and an x squared here? Okay, that means technically speaking, I could solve for this x squared. I could subtract this one over, right? And then stick into x squared. And actually in this particular case, that's what I'm going to choose to do, only because then I know that through that substitution process, I've not only gotten rid of the x, but I've gotten rid of that squared too, right? I'm substituting something in sort of to both of those spots. I mean, I know you aren't technically substituting into the square, right? But they're both going to be removed from my primary equation. And in my mind, that seems like it would be a little bit simpler. Again, as totally personal preference, you're going to end up with the same answer no matter what. So if you want to go ahead and take this x squared plus 1 and stick it into y, that's fine. Okay, in fact, some classes, I believe, chose to do that. And so if you want to, you can look through the class notes and you can see who chose to do what. Right? I'm going to go ahead and subtract this 1 over to the other side to get x squared equals y minus 1. Okay, so here we go. We have distance equals the square root of that x squared is going to come out, and this y minus 1 is going to go into its spot. And then we have the plus y minus 2 quantity squared. Again, I want to repeat, if you hadn't caught this within the context of this being your problem, that would have been totally fine. You could definitely take this x squared plus 1, stick it into y, and you'd be fine. In fact, we'll do that on example 6. We'll just leave it and substitute it into y. Okay. At this point, now that we've substituted it in, we're in terms of one variable. Now it's going to mirror what we've done in the prior problems. We're going to take the derivative, set it equal to 0, and solve. Okay, I don't like having to do a double chain if I don't need to. This is a really easy one to FOIL out. I would recommend foiling this. Simplifying that square root as much as possible before you take your derivative. Okay, so we have the y minus 1 plus, when you FOIL out y minus 2, you get y squared minus 4y plus 4. Which is the same thing as y squared minus 3y plus 3 to the 1/2. When you simplify this up, and then I went ahead and rewrote it as a 1/2 exponent instead of the square root, just because I know eventually I'm going to be taking the derivative. Okay, so now we've got our derivative. We're going to set this equal to 0. Let's bring down this exponent. So we're going to bring down that 1/2. Leave the guts alone and subtract 1 from the 1/2. Then times the derivative of the guts, which in this case the derivative of the guts is 2y minus 3. I'm going to go ahead and rewrite this. We have the 2y minus 3 on top. The 1/2 means that a 2 is on bottom. And then a negative exponent means that is also in the denominator, y squared minus 3y plus 3. Okay, so we have a fraction equal to 0. We're wanting to solve for y. Well, when you have a fraction equal to 0, this goes back to what we've done in Unit 3, which is there's only one part of that actually has to equal 0, right? The only part that actually has to equal 0 is the numerator, because 0 divided by anything is 0. In fact, if the denominator equals 0, that doesn't equal 0. That equals a non-existent point or an indeterminate point. Right, so we want our numerator to equal 0, and so I'm going to go ahead and pull out this numerator here, that 2y minus 3. Okay, and so then when I add 3 to the other side, I get 3 equals 2y, and divide by that 2, I get y equals 3/2. Okay. So what are our desired quantities? In this case, we're looking for our point or points, right? If there's more than one, so they do want a full coordinate point. We have our y coordinates. They also want to know what's our x coordinate or coordinates, depending on the case, right? So my y is 3/2, which again, this is where this x squared equals y minus 1 is going to come in handy. We're going to go ahead and take this 3/2, we're going to plug it in. Okay, so go ahead and take a moment and do that. Plug in that 3/2 and solve for x. Okay, 3/2 minus 1 is 1/2. So we have x squared equals 1/2. And then when I square root both sides, I get plus or minus root 1/2. And so in this case, we are going to have two coordinate points, plus or minus root 1/2. Okay, so it's slightly more complicated than what we did prior. Okay, let's go ahead and do one more, pretty much, well, at least very similar to this one that we've just completed. Again, my challenge to you, pause it with each step, try it on your own, then start the video again so you can check. Okay, so which point or points on the graph of f of x equals root x plus 1 are closest to the point 2, 0? So primary equation first. Closest to is a measure of distance, so we're using our distance formula again. And again, we have a very particular point that we're wanting our distance formula to interact with, so we're going to go ahead and take this 2, 0 and plug it in to my distance formula. So we have distance equals quantity of x minus 2 squared plus y minus 0 squared, plugging in the 2 into the x, the 0 into the y. So here's my primary equation. Secondary equation is always the given, or some sort of given fact. In this case, we're given that y equals root x plus 1. Okay, so now we're going to plug in. Again, you could solve for the x if you wanted to, right, to plug in there. Just my personal preference, I don't see that that's an especially efficient step, as opposed to up here, you know, where it's one step, just subtract the 1 over, you haven't lost that much time, and I know additionally that in doing that, I'm getting rid of both the x and the squared, right? Both of those are going to be taken out when I do my substitution. In this case, you'd have to square both sides and subtract the 1 over to solve for x. And it's still just getting rid of one variable, right? That you would still only be substituting into x. You take extra steps, but you aren't removing anything extra from your primary equation. And so personally, I'd probably just leave it as it is in this particular case and take this root x plus 1 and stick it in, right? So that's what I'm going to do. Okay. Again, manipulate before you take the derivative. So let's go ahead and manipulate this, get it as simplified as possible. Okay, when you FOIL out that x minus 2, you get x squared minus 4x plus 4. And when you square the square root, they cancel each other because they're inverses, and you're left with just that x plus 1. Okay. Which then when I combine like terms, I get x squared minus 3x plus 5. Okay, next step, take the derivative, set it equal to 0. So we're going to bring down that 1/2, leave the guts alone, and subtract 1 from the exponent. Then times by the derivative of the guts. I'm going to go ahead and rewrite that before I solve. So we have the 2x minus 3 on top, and the 2 root x squared minus 3x plus 5 on bottom. Again, fraction, the only thing that we need to have equal 0 is that numerator. So we're going to pull out the 0 equals 2x minus 3. We're going to add that 3 to the other side and divide the 2, and that gets you x equals 3/2. And adding the 3 equals 2x, divide that 2, you get x equals 3/2. Desired quantities in this particular problem are is the point if there's only one point, or are the points if there's multiple points. Okay, so we need to go ahead and figure out what is my y coordinate for x equals 3/2. When I take this 3/2 and I plug it in here, I get root 3/2 plus 1, which 3/2 plus 1 is 5/2, and so this is root 5/2. Kind of a little hint here before I end this video. Backtracking a little bit in both of these problems. In both of these distance formula problems, we got to this point where we had 0 equals a fraction. Okay? And we pulled out the numerator, because the only thing that in our fraction had to equal 0 was the numerator, right? Or is the numerator. 0 equals 2y minus 3, 0 equals 2x minus 3. Take a look in both of these problems at where that 2y minus 3 here came from, or this 2x minus 3 here came from. In this case, the 2y minus 3 came from this point, or place, and this 2x minus 3 came from this place. What are those? this 2y minus 3 at the back of this derivative, and this 2x minus 3 at the back. Look at your initial function if you haven't seen it already. Y squared minus 3y plus 3. How does this 2y minus 3 compare to this y squared minus 3y plus 3? Hoping everyone's been able to see that. This x squared minus 3x plus 5 to this 2x minus 3. It's the guts. It's the derivative of the guts, right? The derivative of our guts here, y squared minus 3y plus 3, is 2y minus 3. And the guts here, 2x minus 3. Just a little hint there for your distance formulas, right? Those guts, the derivative of the guts, is what we're setting equal to 0 when we're solving our distance formula, when we're solving our closest. Okay. There you go.